Hello everybody, let's get started. 7:30. We were at the second phase of the same lecture, lecture 8, what we started last day. And now we are supposed to cover the full length of that lecture, which mostly revolves around the sequential element called register, uh, different construction of different type of registers, and which facilitate also the parallel load, serial load, shifting in both direction. And then we discuss about the combinational shifting method with the use of many multiplexers there, and it's called a barrel shifter. Any question around these or any other topic, let me know. Okay, then why don't we start with again the simulation environment and study a little bit on these registers, 1-bit register, and then we will develop one 4-bit registers with this multiple operation capability in it, and then we'll move to see barrel shifter in action in the simulation environment. Let me first share my screen with you. Okay. All right. So we are first talking about constructing exactly this component. Like we know what the D flip-flop is, and last day we actually have seen the D flip-flop in a simulation environment, how with respect to the clock signals, it basically loads the data, incoming data onto the D pin, into the flip-flop, and reflect back in the Q pin. Inside it has this master slave configuration of the latches, and that becomes a flip-flop, positive edge trigger or negative edge trigger depending on which edge of the clock is fed into the master. That's another factor. But in the simulation environment, let's see if we define it in like this. Remember, last day we also defined a multiplexer. Let's say we have one multiplexer of 1-bit multiplexer, 2 input, 2 to 1. So like this, 2 to 1 multiplexer. And then we defined, also instantiate one D flip-flop with a positive edge trigger D flip-flop. And whatever the output coming out from the multiplexer is fed into the D flip-flop, just like this one. Let me note it. Just like this one. This one is your this guy, FF underscore D, and then the multiplexer is fed with Q, like this thing, feeding back onto the 0 terminal, and the external D. So I0 is Q, and external input D is coming onto the I1 of this mask multiplexer, and selection signal being connected with the load signal of this, just like this configuration. And clock is coming into that, and negative edge reset is also coming into that. So this is what we define, very simple gate level register there. And we have, of course, like if we want to explore the definition of the other part, like we have these multiplexer code here, 1-bit, 1-bit 2 to 1, which defines a line decoder, or which instantiate a line decoder with some AND and OR gate around that, and line decoder being implemented at this point, 1 by 2 line decoder, gate level implementation. So This is more like an hierarchical definition of this hardware module. In reality, it is just like this. Like at the end, it is bunch of transistors that operating underlying to, to make this functionality. You can imagine our 1-bit register has one multiplexer and one D flip-flop. Under the multiplexer, it has one decoder, bunch of AND gates and OR gate. Under the decoder, it has inverter, AND gate, etc. And under this, all this logic gate, each of them contains bunch of transistors, as we discussed in the previous lecture, the construction of the logic gate using the logical model of the transistors. So if we flatten out the whole design from top down, we're left with just a bunch of transistors. Your system, digital computing system, if you think that way, if you drill down and open up the whole chipset, any chipset, memory, processor, doesn't matter, what you'll find is a billions of transistors right sitting onto that piece of silicon. You won't find anything like, okay, this is multiplexer, this is flip-flop, this is AND gate. These are all like logical conception that we want to build around these transistor devices to make our understanding easier at the logic domain. That's all. Physically, everything boils down to the transistor. There are other devices too. Let's not go into that. It is mostly the transistor that gives your computer life. Anyway, let's not go into philosophical direction much. Let's stick to business. So we define this 1-bit register, and we define a little bit of 1-bit register test bench. What it does, it basically feed into some clock into that register, and also reset that register at the very beginning, and then it set up this D input D, and we'll see that this D is loaded onto this or stored into this inside flip-flop only if the load is 1. Okay, just hold on a second. Sorry for that. Now we let's run this. I already pre-compiled this, and let's load this into action. Here is the register test bench. All right, goes there. Oops. Okay, let's add the signals. I think till Q would be sufficient. Put the then reset up DL and Q, and we do the simulation. And then let's fit into the window, maybe a little bit smaller. Okay, that will actually help us. Okay, now you see in this point, okay, at this time point, we came out from the reset state to the normal operation state with a D0, I0, that's fine. At this time point, we made D to 1, but L load signal we kept to 0. So this load signal, where is that? This load signal we kept to 0. That means even if we change the value D to 1, this positive clock cycle Q is not following the D. It is not registering that at all because we haven't issued the load signal into that component. Then at some point here, we made that load signal up, which means we want to load it. And now you see at the very next positive edge of the clock, Q follows the D. Q follows the D. So that is the functionality of the register. D flip-flop, on the other hand, whatever comes into the D, it will blindly load and store into the flip-flop upon this clock edge of the flip-flop. But register, we can actually control which bit will be loading and which time will skip that incoming bit. So that's the functionality of the 1-bit register. We can see the next one as well. Like at this point, we made the D to 0. But next rising clock edge, you see the register is still kept the older value of 1. It's still staying at that because the load is 0 at that point. But as soon as we made the load to high, then next clock positive edge, it follows the D and it went down. The Q went down to 0 following the D logic. So that's your register. Question? Okay, now moving on to the next one, which is like, okay, we discussed about several things here like parallel load and then scanning, the serial load, and then we have this daisy chain connection between the flops so that bits traverse in one direction to other and so on and so forth. But at the end of the day, we came up with some complex register. It's a 2-bit register, which has shift capability in the both direction, also parallel load, also serial load, and that kind of multifunctionality. Let's try to define it in the Verilog, in terms of Verilog, where it's a little bit different than the one proposed here. First of all, it's the 4-bit, just to make the life interesting and observation interesting. So that means it has 4 multiplexer instead of 2, 4 4x1 multiplexer, 1 bit, and followed by the 4 D flip-flop, positive edge D flip-flop. And functionality wise, by the way, it doesn't have the specific scan in per se, but what we did for the left shift and right shift operation, this Q0 follows the D0, as if D0 in this case act as a scan in, SI input in this specific component that I defined here. And for the right shift operation, Q3, the MSB follows the D3. So D3 in that right shift case, it's act as a scan in this case. That's the only difference, I think. Or may not. Like there is a code also, this mode also a little bit different. 0, 0 is a hold, 0, 1 is a parallel load, and serial load, left shift is 1, 0, and right shift serial load is 1, 1. So that's the definition here. And it's just a bunch of these top level, high level component, 4 multiplexer, 4 D flip-flop. We connected accordingly what we want to do. You see, like if it is a parallel load, so by the way, like each of these internal D flip-flop is connected to the output of the multiplexer, which I defined as a like a bus, RD bus. And this RD bus is of the 4-bit RD bus. And this 4D RD bus is, see the multiplexer zeros output goes into the first flip-flop, and then next one, then next one, and then next one, so on and so forth. So this is for the parallel load, not parallel load, sorry, I take it back. This is whatever coming out of the multiplexer. The magic lies in the multiplexer connection. You see, if it is a selection of 0, it is the itself, it is loading itself, the Q0 coming back to itself, like through this multiplexer. So if it is a 0 selection, that is the hold, Q0 is feeding back into itself, thus for the next flip-flop Q1, Q2, Q3. So this is your hold connection. That's how we implemented the hold feature in this register. And then parallel load, the 1, that means my data for flip-flop 0 should come from D0, and data on the flip-flop 1 is D1, and actually I am wrong there. It should be I1 dot D3. It should be D2, D3. Okay, D2, D3. Okay, so that I fixed. Okay, so this is like D0, D1, D2, D3. If it is selection of the I1. Now I2 is left shift. That means left shift is from LSB coming into the onto the LSB side. So that's what the connection is. Your Q0 follows D0. That's what happening here. Then flip-flop 1 or Q1 follows Q0. Q2 follows Q1. Q3 follows Q2. And then I3 is just a reverse order, which is right shift, MSB coming onto the LSB side, and Q3 follows the D3. That's what happens. Q3 follows D3, Q2 follows Q3, Q2 follows Q3, Q1 follows Q2, and Q0 follows Q1. So through this multiplexer connection, we are making these operations, or actually I should say these operations there. Question so far on this module definition? Okay, now let's look at the register test bench. So I have this clock, which is everyone, I think you guys are familiar of, but each 5 nanosecond it toggles, and then register what is, oh sorry, this one is the same thing. Okay, clock, and then we instantiated that 4-bit register into our test bench, driven by a 4-bit D and 2-bit operation and 1-bit clock and end reset. Negative reset, we resetted the whole system first, and then feed in the clock and set the D0 to 0, operation code to 0, which is hold at the initial time. And then at the 10 nanosecond, we are taking out the reset signal, so everything is normal operation. And then at some point of time, we are setting D to 15, and then parallel load. After some time, we are setting D to 12 with the hold operation, and then we are setting D to 0 with a like left shift operation, right? Is it? Yeah, left shift. And then after some times we do the right shift operation. And let's see what happens there. Since I changed the code, I need to recompile at least the changed code. Okay, and then let's pick a 4-bit test bench for our simulation. I think I don't need, I need this. Then let us do this clock on D operation. Let me put this up and reset. Maybe I'll put this up there. Okay, all right, let's simulate. And let's try to understand what is going on here. Maybe this guy. Okay, now you see till this point it is reset operation. Your Q follows, like Q is resetted to all zeros. It is a single bits, right? And so basically Okay, all right. So initially it was all 0, right? Duplicate 0, 0, 0, 0. Okay. Now at this point, okay, why don't I just change the radix to unsigned? Okay. Now at this time point, we changed D to 15, and it's a load operation, right? So D to 15 means it's all 1. D was 1, 1, 1, 1. So this is binary representation of 15, and we load it. Like its operation code changed to 1, which means parallel load. So at this clock, you see your Q become 15, which is all 1. So this becomes 1, this becomes 1, this becomes 1, this becomes 1. So Q now, that register, 4-bit register, is holding a value, represented value of 15 in unsigned form. Okay, now at this time point, we changed the D value to 12, okay, which is like this becomes 0 and this becomes 0. But also we made the operation code to hold, like operation code becomes 0, that means hold. So at this clock cycle, Q value did not change. Q actually storing the previous value of 15, represented value of 15. And then at this time point, we made it a left shift. Left shift means it's basically shifting in this direction, right? This direction. And as our code convention, what we said is that your Q0 will follow, your Q0 will follow D0. So what does it mean? That when that next clock comes in, this guy thrown out, this bit thrown out, this bit to 1, this bit to 1, this bit to 1, and this is replaced by duplicating the D0. So this value is 12, 16. No, not 12. What is that? 8, 4,
14.
Hello?
Was it 14?
Yeah, 14. It is 14. Yeah, one less. Yeah. 12 plus 2. This is 2. Yeah, 14. This is 14. So that's what's happening here. And since we kept that left shift signal alive also in the next clock, this guy is thrown out. This shifted here, this shifted here, this shifted here, and this is duplicated. So this has become 12. And thus in the next cycle, okay, so this guy is shift out, this guy is there, this is shift, left shift, and duplicated. And that's the 8. So this is the 8 value we are getting. And now in this point, we actually reverse the shift direction. We basically said that, hey, now at this point, we do a right shift. And remember, right shift follows the D3 bit. Oh, by the way, D was 0, right? So I need to change these guys to D was all 0. 0, 0. Okay. So Q3 will follow the D3. So what happens in the next clock, in the right shift, this is thrown out. This guy come here, this guy come here, this guy come here, and this is duplicated. Thus, similarly, in the next clock, thrown out, this is here, this is here, this is here, and this is duplicated. So this represents 2. And this clock, further one more shift, thrown away, this one, and this become 1. And the next clock, this one will be thrown away, coming here, 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 and duplicated. Okay, so one observation to be made here in this operation, that number of bit we want to shift is same as number of clock we need to spend time 2. So if it is a 4-bit shift, like it's from 8 to 0, it is a 4-bit shift operation. For that, we need to spend 4 clocks to do that. So 4 into that time period. And that's where the combinational shifter comes into action. Okay, combinational shifter, it's basically instantaneous. It's not instantaneous. It has these logic gate delays and all this stuff, but let aside, it is not depending on clock. It basically, as you present, okay, I want to make a shift of this much amount on this bit pattern, it just give you the answer. Like one combination is like this, and we simply, it is by the electrical connection, how we shift at stages. Okay, question. So far, so good? All right then. Now let's look, then move our attention to this barrel shifter, combinational shifter in the simulation environment, and let's see how we can make it. So let me share my screen once again. Screen 1, this one. Okay. So this is a complex configuration, especially if you go to the number of more bits onto our configuration, like 8-bit. It has a lot of multiplexer we are talking about to carry on this whole implement whole of this barrel shifter. Imagine what if you need to do the 32-bit barrel shifter, and you'll be doing it in project 3. It is a part of project 3 to make a 32-bit barrel shifter at the gate level. So we'll have that fun after the midterm. But anyway, let's move on. Let's do a 4-bit shifter just to counteract this sequential shift operation. Let's see how we can make a barrel shifter in the combinational logic. Okay, in the simulation. Combinational shift. So this is, let's say, so first of all, combinational shift has to make a separate shift circuitry for right shift and left shift. We cannot do it in a common way. Maybe we can think of in such common way, but okay, let's not go into there right now. Let's separate them out to leave out some of the complexity out of the way. So here we are talking about 4-bit, but configuration is the same. It's a 4-bit right shifter, 4-bit left shifter. We have a multiplexer to select between 2 input, like 2x1 4-bit multiplexer with a control of selection, whether left shift or right shift on the result part. But the details explanation lies in the implementation of the connection between the mux. So it's a 4-bit shifting. That means I can shift between 0 to 3-bit of beyond, 0 to 3 decimal value. Shift by 0-bit means no shift, shift by 1-bit, shift by 2-bit, shift by 3-bit. Anything more than shift by 3-bit will result in 0. We'll handle it separately. But let's say our range of shifting, number of shift is from 0 to 3, which is like a 2-bit represented by 2-bit. So this is my shift amount 2-bit. This is my input 4-bit, and this is my output 4-bit.
Professor,
Yes.
are you sharing something else different from your lecture folder? Because I just see your, I guess your folders, and there's
We
nothing
just
else.
see your desktop.
Yeah, you just see your desktop and that's it.
Oh. That's interesting. Let's see. Just hold on. Share. Okay, share. Do you see my model sim window?
Yes.
Yeah.
Okay, maybe something went wrong previously. Okay, so what I was telling is that since my shift is like bound by 0 to 3, we cannot go beyond 3-bit shift because it will anyway result in 0 if we go beyond that. So we restrict our shift amount to be 2-bit with the input of 4-bit and output of 4-bit. Now, connection details is this. Like if my selection, if my shift amount at that stage is 0, means no shift, then we'll just follow through the input. Otherwise, we'll try to do some shifting. And in this case, we have like 2 stages of shifting. It is a log base 2 of 4. 0 to 3 is the range. So log base 2 of 4 means I have 2 stages of multiplexer, stage 0 and stage 1 multiplexer. And this stage 0 will shift by 1 bit, shift to left. And this one will shift, if it is on, will shift by 2-bit, shift to left. Now let's see. So your values are represented with this thing, right? No, absolutely no shift, 0, which is like 0, 0. Now 1-bit shift is 0, 1, like S is 0, 1. 2-bit shift is 1, 0, and 3-bit shift is 1, 1. Right? The S is 1, 1. So for no shift, what happens? Each stage will not shift anything. How it is accomplished? 0, 0 means your S0 is 0, S1 is 0. And under that selection, for each of this multiplexer, I am selecting the input itself. Whatever incoming input, I0, just go pass through that multiplexer. So next stage is feeding with simply that same bit pattern of I0, I1, I2, I3. Now, if it is a shift, means let's say 1-bit shift, okay, or 3-bit shift. At this point, my S0 is 1. Like at this point, is S0 is 1. So I need to do a 1-bit left shift, and we assume that from the LSB side, a 0 will be inserted into the shift position. So my I1, the first multiplexer input is going to be, I select to be 0. And then the next multiplexer, I connect the I0, I1, I2. So as if we are basically, by the connection of the wire itself, we are shifting the bit position from one place to another towards the left. So this is just by connection. And similarly, in that second stage, you see, since it is a 2-bit shift to the left, the first 2-1, if it is no shift, okay, whatever is incoming is going out, no shift at that point. But if it's a shift at this stage, we need to shift out by 2 bits. That means your multiplexer 2 has to be connected with the 0th incoming bit, S0 out 0, and S0 out 1 to the next bit, with first 2 LSB becomes 0. Imagine if it was like a next stage, which is like 1 bit shift, 2 bits in next stage, third stage multiplexer would have been 4 bits shift. Like if it is a 8-bit shifter, we need a 3-bit shift amount. We need 3 stages of multiplexer. The third stage would have been 4-bit shift to the left. Okay, question at this point? So we are simply trying to achieve this one. Okay, just multiplexing, shifting by 1 bit, and then next stage shifting by 2 bit, introducing 2 zeros at the LSB side. That's what we are defining here. And similar way, we do the right bit shifter definition. So this one is like, if it is on, then 1 bit shift to right, and next stage would be 2-bit shift to right. Okay, and the mechanism is the same. Basically, we are trying to do this one. Okay, so on, if it is no shift, it follows the input. If it is a shift, the MSB is 0, and then it successively follows I3, I2, I1, and I0 is thrown out of the picture, and so on and so forth. And once we do these 2 basic elements, then we instantiate that to right bit and left shift into one component, and then have a 4-bit 2x1 multiplexer. Actually, I used 4x1 multiplexer because that was defined earlier. I didn't have 2x1. I could have defined it, but I want to show you something. Even if you don't have the right component, you can still use it in the real electronic world and also simulation environment, that we still use 4-bit multiplexer with the S1 selection higher bit is connected to 0 always, and S0 to the LNR. So as if we are using like 4x1 multiplexer, 4-bit 4x1 multiplexer, but one of the higher selection bit tied always to 0. It is never going to select between the I2 and I3. It will always be selecting between I0 and I1. And thus, in the I3 and I2, I just grounded it, basically. Electronically saying I grounded it, logically said I connected to 4-bit zeros. And also note, there's a notation 4-bit decimal, D is 0, and followed by the values, it's basically a decimal value. Whereas this tick B means that follows digit pattern is a binary pattern, not the decimal pattern. But anyway, that's a side note. So I add the S0 to the LNR, tying off the higher input bits to all zeros, and lower bit I0 to right shift result, and I1 to the left shift result. So it's my functionality is that if LNR is 0, it's a right shift. If LNR is 1, it's a left shift. So thus these connections are. And that means you notice that in the combinational shifter, we always compute the result, both of the right shift and left shift by that amount. But at the selection, we only select whatever is needed, whatever is asked to that component. Result is computed internally, and this component produce the result to the outside world as requested through this control signal of LNR. All right, question. Okay, let's compile. And about the test bench now. So this test bench is very simple. Where is my test bench? Here. So I have left shift tested separately, right shift tested separately. But anyway, interesting is that combination of the shifting. So I have instantiated that combinational shifting and then started with some value 15 as input and shift amount of 0, ln 0. And then I tried a shift amount of 0, 1, 2, and 3 with left shift and right shift alternate. Okay, and let's see how it works. Let's load it, which is shift db. Shift db. Okay, let's put them. The radix to unsigned and simulate. Okay. Now you see, like we have the input 15, like I just kept it. And then shift amount, okay? Shift amount is 0. That means whether it is right shift, left shift, doesn't matter, LNR. If it is 0, it is left right shift, otherwise left shift. But since the amount is 0, doesn't matter. But as soon as I change the amount to 1, our 15 right shift would amount to 7, right? It becomes like, you should do the mental calculation, 15, 4-bit 15, you shift to right with a appending 0 onto the MSB, it becomes 7. But if you do the other way, left shift, then the MSB will become 0, everything else is 1, so that means 14. So 7, 14 comes off here. With a 2-bit shifting, similar logic, right shift would result in 3, left shift would result in 12, and 3-bit shifting, right shift would result in 1, and left shift will result in 8. So you see, like there is no clock dependency in zero delay model. There is no weightage. As soon as you are querying this module, this circuit, that hey, compute my shift amount, it just give you the answer back through that maze of multiplexer. Something like, yeah, something like this complex one. Right shifter and left shifter. Imagine how complex it would become for the 32-bit barrel shifter scenario. Question? Okay, let's take 5-minute break and then we'll be back. Okay, let's get back, and it is a pop quiz time. Please go to your canvas and find there is a pop quiz 3. Click on that, and whenever you are ready, then answer this poll to yes, that you are ready to enter the passcode. Once everyone is ready, then I will, yeah, I'll send another poll with the passcode. Okay, so far 28 of 45. Okay, all right. 43 of 45. Maybe I'll just wait a couple of more seconds. Okay, let me share the quiz password. See if you can use it.
Worked.
Professor?
Hello.
Professor, I had a question.
Yeah, tell me.
For question 8, I don't see where to input and answer. It's just bracket ANS bracket.
Oh, if you have that, okay, just leave it like that, and you can send me an email. I'll look at your case.
Okay, thank you.
Okay.
Do we leave after we completed the quiz?
Excuse me, what's your question?
Do we leave after we completed the quiz?
Yeah, I think I will touch base on the projects and stuff like that. But yeah, it's you can leave if you want.
Oh, we're gonna talk about the project.
Yeah, I like to see how far we are in the project in our class. Just see if anyone has any question around the projects.
Okay, got you.
It's up to you.
No, I'll stay. I'll stay.
Okay, I think time is up for most of you. Uh, let's quickly review the scores. Let's start. Hey.
When did you say you'll publish the scores?
Yeah. So I see I'm just sharing these quiz statistics. Pop quiz 3, high score 100% with the average score 60, which is alarming as a class. Please make sure you're up to date with your study on this part. So that's all, and I will open up the answers and the scores to you tonight after the class. Okay, I want to talk about, or at
Professor?
least, yes.
I had a quick note about the quiz.
Uh-huh.
On the first question for me, it only showed 3 logic gates, but like I had to scroll over to see the last one, and I didn't notice that at first. So that might have been confusing for a lot of students.
Yeah, please send me an email. Yeah, I didn't know that but the scroll bar was there, right?
Right, but it only showed
Mm.
3. It was hard to see the 4th one.
Mm-hmm. Okay, I see. Yeah, maybe it's if the screen is smaller, I don't know. I need to check. Please send me. Okay, send me an email. Okay. How is the project 2 going on? Any comments from any student? Have started, not started? No, yes, maybe.
It's a work in progress.
Yeah, let it be work in progress. There are milestones, and please make sure if you haven't started yet, please do start now. This is probably the latest time you can manage the project in time. Otherwise, you'll have a big problem. Okay, so I don't know, like if someone has started and just experiencing that project, maybe if you want to share your experience and like your thought and your tips for the other student, that would be much appreciated. Anyone wants to volunteer about that? Like your initial feeling about this project too?
Please do share. I haven't started yet.
Okay, please, Yorick, please make sure at least you go through the requirement and at least go through the guideline document soon and start on the project coding right away.
Professor.
Yes, Laura.
Yeah, for me, I did start the Razor file, but it's not compiling at the moment for me. So I don't know if.
So you can send me what's error you are getting.
So that's the thing. That's what I wanted to ask you. Like, I don't really see. It just said I have 2 errors, but is there any way that I can go and check where I'm getting the errors? That was my.
So that on the red message, if you double click, it will pop up a window. It should pop up a window and give you the line number, source code, etc.
Oh, I see it. Perfect. Thank you.
Okay. All right. If we don't have anything else, so that's what I just wanted to mention. If you haven't started on project 2, please start. Please make sure you are with the as par with the milestones have been established. Milestones are optional, but this is just a guideline that you are on the right track. Saying that, then good night, everybody, and see you on Thursday.
Professor, I had a quick question before you leave. I'm not sure if you got my email, but it's regarding the course modules that you have posted on Canvas. So do you want us to like click through each and every single one of those links? Is that how we get credit, or can we just simply watch your YouTube videos on the channel?
I don't credit on those page views or anything like that. You can watch the videos on the YouTube. You can go through, but the clicking has a significance that it unlocks the next module, or the assignment is depending on that module. It won't be unlocked unless you click it. So click is more like a ceremonial thing to do.
Okay, okay. But it won't like negatively impact our grade if we don't click certain links, right?
No. It's basically, yeah. Only that unlocking of the next module depends on the page you clicked. It tracks the theory pages that you click, and then only all the click has been made, and then only it unlocks the next module.
Okay, okay. So it's just for us to keep track, nothing more than that.
Right.
Okay.
As long as you are watching the videos or getting
Yeah.
I'm okay.
Okay, sweet. Thank you.
All right, and then